Hello and welcome to our next vlog or podcast related to electric machines. We're going to return to the topic of our new technology, the EMPOWER. I just finished this week doing a training class down in Texas and again heard comments related to the discussion that you cannot test a motor unloaded with electrical signature analysis, and then also got to hear about the shortcomings of motor current signature analysis. So when I looked into the sources, I discovered that, of course, it's people, even people within that industry, that are clueless when it comes to electrical and current signature analysis. And I believe that's probably one of the primary reasons why the technology has been held back so much. What I will say is we use virtually every technology that you can think of for electric machinery testing. If we don't have it in-house, we lease the equipment and perform the analysis. That, plus I sit on virtually every standard. So what ends up happening is opposition to the implementation of ESA and MCSA is snuck in other standards. Including some trade associations in which people are, bought into certain technologies. So the attempt from a commercial perspective to prevent another technology from coming onto the market. We add on to that some existing technologies have shortcomings, and they're significant shortcomings in that you need 60 or 70% of load to test anything. Well, I'm sorry to say, folks, I've been testing with electrical signature analysis and current signature analysis for decades. And a lot of the time I'm doing in-shop, meaning on the shop floor, testing of machines on test beds at full voltage. So in this case, in the class, we were using, the class was on the EMPATH. They purchased the EMPATH. But I went ahead and ran the EMPOWER alongside it, and we detected every single condition in those machines. So we're going to get into two of the machines. This one here, which was the first one tested. Now, just like before, there's going to be a pause because, again, I'm still using the system for recording these, so everything gets bound up. But in any case, I'm going to pause when there's the approximately 2-minute stretch of the software running. I will start it up immediately before it produces its results. So everything I show will be raw. Now, in the first one, this was a motor sitting in their spares. And in the second one, it is a cast aluminum 4,000 volt 400 horsepower GE machine that came in from a customer the evening before. And so this is literally the first time it was being tested. We did the Megger check on it. We made sure the winding wasn't shorted, and then we tested it. So there was no other testing other than vibration. So they had mounted their vibration probes on it when we took the testing, and the vibration didn't detect anything. So we'll go through that, and I'll explain why. You will see electrical stress readings come up, and that's because of the particular soft start they're using. It's called a Benshaw, and it uses SCRs, and it just leaves them open when it gets up to speed. Now, I'm not doing inrush testing with the EMPOWER, although there are some tricks you can do it now. We're going to have that ability built in later. So in any case, let's go ahead. Let's get started. So this machine here is the first one we're talking about. This is a 300 horsepower machine. So let's go ahead and we'll pull up the EMPOWER data. So let's go ahead and we're going to open up that machine. So that was done on the 6th. And then it was a Reliance motor, 300 horsepower. So I'm going to go ahead, open up the data, show you what we're looking at. This is completely unloaded, as you see right there. just 4,000 volts coming to it. 4,000 volts soft started. Just so you can see what it's doing a lot of stuff in the background as it's opening up each spectra. So it's not as fast as some software, but we're really going through and just scrubbing that data and looking at it. We're not getting rid of anomalies and outliers. We're using standard filters and everything else, making it quite interesting. So as you can see, not a lot going on here. Now I'm going to go ahead and we're going to hit auto analyze, and then I'm going to pause the video. So auto analyze, it's getting started right now. Can't move that window over, but it tells me, it's going to take 2 minutes. This will pause as our proprietary bits run. Okay, so here we go. You can see it's doing things in the background. It's picked out the speed already. It's done a few other things. It'll occasionally give me a memory thing going, and that's primarily because of the RAM. But in any case, so it's picking out everything. It's also setting up the losses in watts for each point that it's identifying. So each bearing point, the pole pass frequencies, the any one-time RPM stuff, all of that, and it'll always have some level of wattage. So we're gonna take a look at that. So here it is. It's completed its analysis. It says check rotor bars, unbalanced or misalignment detected, winding stress. The winding stress is showing up because of the controls. It does exist. The peaks are there. So let's go ahead and take a look at the rest. So unbalanced or misalignment, there's my one-time RPM. Now these peaks we discovered were related to the to the soft starter, so those will be ignored. This has got Babbitt style bearings, so it will not show any type of bearing condition. So let's take a look here. This is the watt analysis basically, and we're gonna take a look here and see. So because we had to set up to a CT, so this is including off of a CT going into their controls for monitoring. So 100 millivolt per amp because we set it for 20 amps, and then the CT ratio of 225 is what was required. Now we've set motor nameplate information. Now we're going to assume 6,000 hours of operation at no load uncoupled so that I show some values. Let's go ahead and take a peek. Okay, and we will, so here's my losses. Pole pass frequency had about 680 watts. Speed, the one-time RPM was carrying slightly more than I would have expected, but we could tell it was unbalanced. And then the stator slot and rotor bar did not see significant losses there. So if I say, okay, that's going to be about 5 megawatts, I'm sorry, 5 kilowatts worth of its operating stuff. So it's about 36% loaded. There's the, operating stuff, basically what it operates at. I don't put a dollar figure up here because, and then down here, it basically says, in these conditions, this is what all the losses come up to, and that's bad. Okay, so that's it. So we were able to detect certain things, and then we can zoom in to verify stuff in here. So this was a nice one. You can see it's a 2-pole machine, so it won't become synchronous. It was very, very close, 3595.66 or 3595.7 RPM. So let's go ahead and we're going to pick out the next machine. So I'm going to manually get rid of this. And then let's go ahead and pick out the other machine, and that's going to be my GE. And I'll show you what that looks like in just a second here. So let's go ahead and open the data first. This will drop to some other value. Now these screens here, this is done by the software, so they're not editable. Motor speed, if I disagree, I can put in a different value. Okay, there we go. So yeah, so here's our information. Just under 12 amps, 60.03 hertz and everything else. It hasn't run any analysis yet. Motor nameplate is 400 horsepower, 1785 RPM, 4,000 volts, and I set everything else up the same way. This one does have ball bearings. So let's take a look at that machine real quick. Okay, so here's the machine. It's a 400 horsepower GE. It's a little older. The vibration stuff's back here. That'll be put on here. This is the picture we took while it was being set up. This is where we had the system connected. So this is the EMPATH laptop getting ready to do an inrush analysis as well. So we set it up, set the trigger. So this is the customer's system, including their EMPATH. So that's set up back here. There's data coming in from CTs and PTs, so both voltage and current were connected there. There's the EMPOWER getting ready because we're going to set up, my laptop will end up going up here to collect that data. So let's see, yeah, we'll show what the results came up to afterwards. So let's go ahead back here where we are, and we've looked at this. So we're going to do the same thing. You can see that there are some peaks here and so on. So we're going to go ahead and let it run the auto analysis. And let me get that other one in back. And we hit it, and we'll pause. Okay, and here we go with the analysis finishing up after it's... Most of that time is it picking out the speed, because unlike vibration, I don't, if I have a bin of, 20 RPM in vibration, I'm good. With ESA and MCSA, we really do want to be very, very close to the speed. And the good news is there's usually a small peak in running speed, and sometimes a corresponding peak, or most of the time, corresponding peak in pole pass frequency. So we're going to take a look at that as well. So let's see what it picked up. As you can see, the RMS current's about 12 amps at 4,000 volts. It's almost there. So it's calculating out right now the exact frequencies and then also amplitude. So here it goes. I have bearing defects in this case, primarily. Let's go ahead and take a close look. It gave me a speed probably a little too low. So let's go ahead and take a quick look and see where it selected things to make sure that maybe it is running that slow. There are definitely bearing peaks there. So let's let's zoom in. I can zoom in either up here or down here. Let's just use this one for simplicity. Okay, so it's out there a little bit, and it looks like I actually have some peaks close in. So let's get up here or let's go back, and then let's go into where it detected speed. So this would be somewhere around 90. Yeah, so that did not fall on the right peak. So we are going to be right about here, which would be 89.95. So 89.95, which is actually subtract 60. That's 29.95. So 29.95 times 60 gives me 1797 exactly, like no decimal places. So 1797. So let's go ahead and reanalyze with 1797 with an input one from us. So this is my input now. So it's going to run another analysis. And you can see it went immediately into the part where I just restarted the video because, you know, I put in a known value. I could have done that right off the bat, but, you know, so it was off by about 20 RPM, probably because the peak is almost non-existent. But it is possible. Now, we couldn't hear anything wrong with the machine, like there was no sound indicating any type of trouble. The other data set, by the way, did pick out a number, because I took two sets of data very, very close to this. And that was the data set taken immediately after we started it. Okay, come on. Almost there. Okay, we are doing kilowatts, so it's going to pop those up. Okay, so check rotor bars. So let's go in now and take a peek and see what its doing is. And so what I did is I left the software set up, so it leaves the original ones and the new ones. So I'm probably showing a little too fast because it's kind of in, but there's the peak right there. So nope, got it pretty much right on. It's just on the outside there. So just a slight change. So there's where the other one was, and there was this one. So I mean, really, the condition's not that bad, and there's no unbalance in it. Now the vibration data also picked up there were no issues in it, and yet here I am with bearing defects. So you saw nameplate. So let's take a look and see what it says. So here we go. I have a pole pass frequency with some peaks. That's right off of the peak in close. I have a ball loss of 596 watts, and on the opposite drive end, 599 watts. That usually goes along with a loss of lubrication. You know, something not quite right there. Dry bearings is what I usually say, because all my other readings are relatively low. Now I do have an outer race slightly higher here, which means on the opposite drive end, meaning that there's now damage with that machine. Usually if I see an outer or inner race defect, that indicates that. So cage sometimes will be a little elevated. It is down here, not so much up here. And then, you know, usually 20 to 40 watts in a machine of this size is just straight friction and windage. But I have an elevated ball, which means it's having to plow through, you know, dried out soap or something. So let's see what it actually looked like. So here's our drive end. Okay, right here you can see caked grease, and you can see a dribble of grease down here, of oil I should say, because the oil's leaking out of the grease. It also looks kind of muddy, almost like there was water or something in there. This should be rounded off, and instead I've got caked grease on it. That's not expected. You can see some fretting on the outside too, meaning that in operation it's dragging a little bit. And here's my cast rotor, and you know, whenever I have an unbalance, there's the can't see it right behind here is a large amount of balancing weight, and then they lightened it up on this side by removing material. Okay, same as on the other side. So that's the bearing as a direct result, so we detected that. But the opposite drive end bearing should look similar. And here it is, definitely caked on, a lot more fretting going on this side. I'll show you what the housing looks like in a second. So when I saw this, I noticed some different colors in here, and I said, I wonder if they mixed incompatible greases. So we walked over to the end shield, and this is what we saw. So this is where the grease comes in, and you can see this is a completely different color. It's not quite white enough to be a lithium grease. It's possible it is. It's definitely not the kind of bluish standard polyurea that's in here. So this is definitely something else. And you can tell that it's grease incompatibility because all of the oil was expunged or expelled from the grease. So they had a fair amount of grease in here, but it was primarily dried out and very cakey. And the oil had leaked out and into the machine on both ends. So that was kind of it. You can see a little bit of the fretting on the inside too that matches up with the markings on the bearing. The drive end, basically the end shield came off very, very easily. So that was about it. Just wanted to show you that, you know, the detection capability of the system, especially when the vibration equipment that was mounted on here didn't see this at all. The customer sent it in. We don't know why. Unless there was some bearing noise at some point in time when everything would start to heat up. Wasn't out of balance, obviously, because I had a hard time finding the running speed automatically because it looks for peaks. We have figured out how to get around that. So in version 1.1, which will come out in about 8 weeks, is going to have that correction in it, along with a bunch of other stuff. We're trying to streamline it so it goes a little faster as well. So right now it takes 2 minutes to collect data. That's not going to change. And then it will do the rest. Now, why is this that we can detect things at a certain in a certain way? And it comes down to this. It's all about the resolution. Okay, so if I have, and then you can see this cuts off at 5 kilohertz. Well, I deliberately cut it off. There's no roll off here because we're actually taking data at 44.1 kilohertz. So the highest sampling rate in ESA right now. The EMPATH takes it at 12 kilohertz, which was the highest sampling rate. Everybody else is taking a shorter rate. So in order to figure out what my resolution is, I take the number of samples, so 44.1 kilohertz, and divide it by the number of samples times the seconds. In this case, we're going for 120 seconds, so I do that over that, and then that gives me my, 110 actually, because what we do is we lop off the first 10 seconds because we're working on a way to filter out the just like with vibration. When I first put my transducer down, it's got to settle, so does this. So we're working on that right now, because if I connect and I immediately take data for the first few seconds, I get all kinds of weird stuff. So we just lop it off. Now I have done them where we run for 20 seconds and then the machine shuts down. I can still analyze that. My resolution just isn't as good. So this is optimal for 0.009 hertz across the entire low and high spectrum. We do sometimes get a little drift out here depending on how we're set up. Like in this case, we're connected with on a CT that's not the highest grade CT, so there's a little drift as a result when I come out here, but still, as you can see, flatlined. It's a little elevated, so we compensate for that in the software. And that's it. The reason the 0.009 hertz resolution is the key, whereas when we're dealing with some of the other ESA devices, whenever you hear them say we need 60% of load, or you need 50% of load, or something along those lines, it's because of the resolution. Otherwise, things like the pole pass frequency blend in here, and you can see we came pretty close to that. That's it. So have fun. I'm glad that you know a little bit more now. I will note one thing too, as well, is when I talk about these losses, even under full load, those should not change by very much. Those amplitudes won't change because it's friction. As long as I'm running that speed, it'll adjust a little bit based on speed. And the amplitudes won't change. And I think I've covered that in one of the recent podcasts. Have a great day. Have a good weekend. Happy Veterans Day, folks. Motor Dock is a veteran-owned small business. I served in the Navy in the 80s under Reagan, and that's it.